Hello, everyone. Today we are going to talk about a few important things and quite simple that, based on my experience, I see sometimes my students struggle with, or if they don't struggle with, at least knowing these may help them make sure that the results of their calculations are correct and they can do it faster. Okay? And it's mostly going back to basic geometry and dealing with vectors and a little bit uh, basically triangles. So the first thing is the cross product, right? So we all know that I cross j is k, right? And sometimes, like when I ask my student, okay, what is k cross j? And they sometimes are a little bit hesitant to say, is it positive I or negative I? So I found that sometimes making a mistake on this, which happens frequently in my classes and with my students, it can easily lead to a bunch of wrong answers and lead to future mistakes in your work. So this is what I always ask my students if they are, for any reason, not sure which one it is. Always they can do a traffic circle. So what I ask them to do is to start with I, and like any traffic circle in real world, they go counterclockwise from I to J, and then from that to what? To K. Okay, so this is a traffic circle where you can go from I to J to K in a counterclockwise manner as you do in real world. And now, whenever you do a cross product, you can always check with this traffic circle. For example, here, if you see I'm doing K cross J, you know the cross product does not have the commutative law, right? If you reverse the order, you're gonna change the sign of the result. So I'm doing K, I'm going from K to J, so I'm going like this. And when you go from one vector to the other along the circle, you would definitely, the result is going to be what? The result is going to be definitely the next one, but if you look, you're going opposite to the direction of the circle, right? In real life, if you go opposite to the direction of the traffic circle and there is a police, they give you what? A ticket. So here, that's the same. If you go against the direction of the circle, you will get a what? You will get a negative. So the result in this case is what? It's negative I. But if I ask you, for example, what is K cross I? When you're doing K cross I, as you can see, I am being a good citizen. I'm going in the direction of the circle. So I will get the next vector. But since I'm following the direction of the circle, therefore I should get what? A plus, because I'm a good guy. So what is the result? It is going to be J, but it is going to be what? Positive J, okay? So this traffic circle can always help you making sure that the result of the cross product is correct. That's one thing. The other thing is, when you're doing the cross product of two vectors that have most of the time all the three components, so let's say you have vector A and vector B, and let's say, for example, you have A to be like 2I minus 3J plus 1K, and then this one is like negative I plus 2J and then plus 4K. So whenever you're doing the cross of these two vectors, let's say A cross B, well, many students, what they do is they do the cross product and they use the distributive property, correct? So what they do is first they cross this 2I with the whole vector B. So if you do that, the result is going to be 2I cross negative I, and then plus 2I cross 2J, and then plus 2i cross 4k, correct? And then they keep adding, like now they go to this negative 3j, so it will be negative 3j cross basically negative I, negative 3j cross 2j, and negative 3j cross 4k. And finally, they go to the last element, k, and now it is going to be plus k cross negative I, and then plus k cross 2j, and then plus k cross 4k. And then they try to simplify the result of this using that traffic circle I just showed you. And now if you do it over and over, it is going to be very easy. And you know that, for example, I cross I, or negative I, that is 0. The same thing happens to j cross j, and the same thing happens to what? K cross k. So these guys are all 0. Now you go to I cross j, that's k. 2 times 2 is 4, so you have a 4k here. And then here you have I cross k, and I cross k, you have to go back to that circle and see that is what? Negative j, so this is negative 8j. Come here, and this is what? J cross k, and j cross k is I. It's 12, and there is a negative, so that is negative 12i. Here you have j cross I, which is negative k, but there are 2 other negatives that cancel, so you still will get negative 3k. Then you have k cross I, which is j, but there is a negative. And finally, k cross j, which is negative I, so it is going to be negative 2i. And now simplify. 2 and negative 2, negative 12, that's negative 14i. Then you have j, there is a negative here, and there is a negative 8 there, so that should be negative 9j. And finally you have k, and k, there is a 4, there is a negative 3, so it should be 1k. And that's the result, right? This is what you do in the beginning when you do physics. And if you want, you can check it with MATLAB, right? In MATLAB, there is the command cross, right? So you have 2, negative 3, and 1. So you do something like this. You say, what is the cross of vector A and vector B, where vector A is, as you can see, 2, negative 3, 1. And vector B is negative 1, 2, 4. And you will get the result that we got, negative 14, negative 9, and positive 1, correct? So you can check it. But what I want to show you is not any of these. What I want to show you is the Sarus's method, or Sarus's law, which can carry out this cross product using a 3x3 determinant a lot faster. So what the Sarus's method saying is, if I want to do A cross B, I form a 3x3 determinant. The first row will be I, j, and k. The second row are going to be the entries of vector A, the elements of A, 2, negative 3, and 1. And then the last row going to be the numbers in B, negative 1, 2, and 4. So it says, if you do it by this determinant, it is way easier. And this is not the Sarus's method. In general, it's always applicable. Now, some students, when they want to calculate this 3x3 determinants, they use the general formula for expansion of any determinant, right? So they say it's, for example, equal to element 1, 1 times determinant of the minor 1, 1 times negative 1 to the 1 plus 1, correct? So they say negative 1 to the, if I expand it with respect to the first row, correct? So it's going to be 1 plus 1 times the element 1 times determinant of row 1, column 1 excluded. So it is going to be this. and then you have to go to the second element in the first row. So it is going to be this, and then determinant of now first row, second column excluded. So 2, 1, negative 1, and 4. And then negative 1 to the 1 plus 3 times k times the determinant of first row, third column. So you get 2, negative 3, negative 1, 2. And then you have to calculate this, correct, the expansion formula, and do it. And we can do that. That's in 1i. This is negative 12, and then minus 2, that's negative 14. Here you have 8 plus 1, that's 9, times a negative 1, that's negative 9, times j, and then you have 4, and then minus 3, that's 1. This is 1, so you will get positive k. And it's relatively good, relatively fast if you do it, but you have to do all of these minors and expansions and everything. Now, the Sarus's method which is only applicable for 3 by 3 determinants, not higher orders. This is the method that can make life a lot faster. So what I'll do is I want to calculate this determinant. And again, to get fast with this, you need a little bit of practice, but once you do practice with this, it is way easier than expanding it. Okay, so here we are going to do this using the Sarus's method. And what this method says is this. Well, let's say here I want to calculate this determinant. All I do is I copy and paste the first 2 columns of this matrix on the right-hand side. So, right, copy, paste. Oh, not Control X, of course. Control C. So, Control C, Control V. Let's see. For some reason, it does not like me to copy. Oh, there we go. Correct. So, you have, let me put these numbers down here manually. Gonna be faster. So I just copied and pasted the first 2 columns of this matrix on the right-hand side. That's all I did. Can be done very fast. And now this method says when you want to calculate it, this is equal to 1 parenthesis minus another one. And let me use some color coding. So this one, and then minus, and here this one. So what does it say? It says the first parenthesis is the product of the diagonal of the matrix. The main diagonal, if you multiply very fast, is negative 12i. Now it says shift this diagonal 1 unit to the right, so you come here. And this is going to be, of course, what? Negative j, then shift it 1 more time, and you get what? 4k. Now, for the negative parts, I go with anti-diagonal. What is anti-diagonal? That's 3k. The same thing you did to the main diagonal, you shifted it to the right 2 times, do the same thing. Here, shift. Let me do it this way. So it is 2i, and then multiply all these 3 guys together, that's 8j, and done. So diagonal and its 2 parallels to the right, positive, anti-diagonal, and the 2 parallels to it to the right are negative. Add them together, you're good to go. Right? Negative 2, negative 12, that's negative 14. Negative 1, negative 8, that's negative 9. And then 4 minus 3 is what? 1. Okay, this method is significantly faster than expanding it about any row or any column, or directly using the distributive method to simplify. Okay, So again, we call it the Sarus method. It is used for only 3x3 determinants, which is what you need for cross products, and it makes your life a lot easier. The last thing I want to talk about in this video is basically the laws of sine and cosine in a triangle, which we use a lot in engineering, in dynamics, and so many applications. I'll give you an application soon, but let me first tell you these. You most probably heard of them, but we use these guys a lot. And these are useful for a general triangle. If you have a general triangle with the three sides being equal to A, B, and C, and the three angles to be alpha, let me use alpha here, beta, and gamma. Okay, so this is arbitrary triangle. No two sides are necessarily, or two angles are equal. Now, the laws of cosine for this triangle says, there are three of it. It says any side squared, any side, the length of any side squared, let's say A squared is what? Sum of the two other sides squared, which is B squared plus C squared. So far, it's just like the Pythagorean theorem. Now, minus 2 times the product of those two sides times cosine of angle between those two sides. Okay, this is called the law of cosine. You can similarly write it for B. B squared is sum of the two other sides squared, minus 2 times the product of them, times cosine of angle between A and C, which is what? Or in front of B, basically. Beta, and finally C squared. Okay? This is B. Minus 2AB, and this is going to be cosine of gamma. So these three, we call them laws of cosine. They are like generalized Pythagorean theorem. If one of these angles is 90 degrees, cosine of it is 0, so the third term goes away on the right-hand side, and you get one side squared is sum of the two other sides squared, which is the Pythagorean theorem. Okay, so it's like a generalized Pythagorean theorem. These guys, we call them laws of cosine, and we use these guys a lot. I'll show you in an example. The other thing we have is called laws of sines, or sine. This one says the ratio of any side to the sine of angle in front of it. The other one is what? B over sine of beta, correct? So I'm dividing each side by the angle of, by the sine of the angle in front of it. It says this ratio is what? The same for all three sides. Right? So there are three equalities here. First one equal second one, first one equal third one, second one equal third one. And these guys, we call them laws of sine. And these are valid for any triangle. And we use these guys a lot, as I said. Okay? You might say, well, like when? Okay, one example was I recently had in my dynamics class. It was like this. So what you had was a pendulum that was originally horizontal, and this pendulum is going to swing down from 0 angle to 60-degree angle, and on this side of it, it is attached to a spring. The spring K was given, this length L was given, and the unstretched length of the spring was given. Let's say this K, for example, was 20, and this length was 0.4 meters. So this is Newton per meter. And then it says the unstretched length of the string, okay, So S naught, or whatever you want to call it. Let me call this A if you don't mind. So I can call the length of the spring L. So A. So L naught, the unstretched length of the spring, is 0.4 meters. And this distance from here to here in this picture was 0.6 meters. Okay, and then this guy will swing and will come down to this configuration where this angle was 60 degrees. And of course the spring is going to be what? Stretched even further. And the mass of this guy was also given. Let's say the mass of this is 1 kilogram, and you release it from rest, correct? So omega at the beginning is 0 radians per second. It says when this angle theta becomes 60 degrees, so it says at theta becomes 60 degrees, and this was when theta was 0. For this situation, you tell me what is omega 2. Okay? And you know, if you use the work energy method, which was requested in the problem, you have to say that the total work done on the pendulum between position 1 and 2 is equal to the changes in its kinetic energy. So, for example, if I call this point A, right, then the total work here, there are how many forces on this object? There is the spring force, if you draw it at arbitrary angle, correct? There is the spring force on it, and there is mg, and there are the two pivot forces, AX and AY, which do not do any work because they are applied to stationary point. The only forces that are doing anything are spring force and mg. So when you say the total work done on this object between position 1 and 2, it's simply the work done by the spring force plus the work done by mg. This is equal to its change in kinetic energy, K2 minus K1. Now we know the formula for mg is negative mg delta y of the center, and for spring force is negative k over 2 s2 squared minus s1 squared, where s here is deflection, and k, if you have a pure rotation about an off-center point, k1 is 0 because you start from rest. K2 is 1/2 times I about point A times omega 2 squared. Okay, so everything here can be calculated. Y of point C, how much it goes down from here to here, right? You can definitely calculate that based on the sine of 60 degrees. So it's going to be basically A over 2 sine of 60 degrees with the negative sign. The only thing is this S1 and S2. So S1 is given here. It is initially 0.6 length. The unstretched is 0.4. So S1 is 0.6 minus 0.4. So that this guy is 0.2, right? And this one, as I said, is negative A over 2 sine of 60 degrees. And I about A is ML squared. In this case, MA squared over 3. So the only thing was S2. For S2, what you needed was this total length from here to here, if I call it L2, and then subtract that from initial L, correct? Now, how would you find it? Well, if you look here in this triangle, one side is 1 meter, this side is 0.4 meter, because that's the same pendulum, and this angle is 60 degrees. Now I want the length of the other side. And the only way to find it is using what? The laws of cosine. So what you have in this case is this triangle. This is L2, this is 1 meter, this is 0.4 meter, and this angle is 60 degrees. And I can clearly say that L2 squared is equal to 1 squared plus 0.4 squared minus 2 times 1 times 0.4 times cosine of angle between them. And from here you can find what? L2, of course. Correct? And then you plug it into the problem and you solve for omega 2 of it. So you see, this is one of the cases that in dynamics we use laws of cosine. Another case that we had a lot and will do a lot is basically when we try to find the center of rotation, instantaneous center of rotation. Finding the location of that in many applications needs trigonometry and geometry. And these laws of sine and cosine are extremely useful, okay? So please learn them. In statics, you also need them many times, and try to use them, okay? Thank you for your attention.